Good morning from the UK. Welcome to the 27th Surface Ventures keynote. Before we go any further, can you please write where you're joining us from today in the chat box on the right-hand side? And while you do that, let me introduce myself. My name's Dr. Tahid Khan. I'm a VP at Surface Ventures, and I am your host for today's session. We are a non-for-profit organization, and our mission is to provide world-class surface engineering education for academia and industry. So every month we bring you a sector-leading speaker to present the current challenges and future trends in surface engineering, alongside surface engineering workshops and live equipment demonstration. So in the chat, it seems to be working. Great, thank you. In many great places there. So today it's my absolute pleasure to introduce Professor Jens Hardel of the Division of Machine Elements from Luleå University of Technology in Sweden. Professor Hardel is the head of the Division of Machine Elements at the university. His research interests are in high-temperature tribology, tribology of dry contacts and surface engineering. He's been a member of the Swedish tribology group since 2011 and has numerous industrial collaborations such as SKF. He is also a visiting researcher at a number of universities such as University de Lyon, Kassel University, Germany, and Atatürk University in Turkey. So in terms of an agenda for today, we're going to begin with our speaker's presentation. We will then have a presentation from Dr. Amina Schneider of Optimal Instruments before a Q&A session at the end of the event. So just a quick note on questions. Please do type these into the chat box and they'll be marked for the Q&A session. We are planning to go for around 60 minutes in total today, but sometimes it does go over depending on the questions. So we do apologize in advance if that happens. We will be offering attendance certificates for live attendees today. The link will be shared later in the event. Also, a quick reminder about our website, surfaceventures.org. It features the videos from previous talks, information regarding upcoming webinars, and information about the Surface Ventures team. We always like to learn a bit about our audience, so there should be a quick poll appearing on your screen. As previous events, could you please answer the question that should pop up on your screen about now? And the question is, what is your current job / position? That's great. We have a nice mix of students, researchers, and managers. So on that note, let's welcome our speaker and proceed with the webinar. Professor Jens Hardel, over to yourself.
Good morning. And from my side as well, warm welcome to this webinar. Thank you so much for inviting me to give this talk, which is entitled Lubrication in Harsh Conditions. And I have a outline that looks broadly like this. I will talk a little bit about metal forming tribology to start with, to sort of set the scene, try to elaborate on some of the main issues that are occurring when it comes to tribology and metal forming processes. Then I will spend some time on a particular problem, material transfer in metal forming, but specifically in hot metal forming. And then move on from there into some suggestions on how to obtain robust friction and minimized galling or material transfer in metal forming operations. And I'll conclude my talk with some general remarks and some suggestions for needs for future research. Before we dive into the technical content, I just want to say a few words about our university. So I am located in the north of Sweden, in the city of Luleå, which is about 1,000 kilometers north of Stockholm. As you can see in the screen, highlighted in red there on the eastern coast of Sweden. Our university is a technical university with 4 campuses distributed in the north of Sweden, from Kiruna in the north to Skellefteå, some 130 kilometers south of where I am sitting in Luleå right now. So just some short facts to put the university into a broader context. So we are a research biased university, as you can see from the split in our budget allocation. We have about 60% nearly into research and about a little 40% in education. We have a turnover of roughly 1.9 billion Swedish crowns. And in total, about 19,000 students, 1,800 employees, and out of those 1,800, we have about 270 professors. We are collaborating with industry to a great extent, and 60% of our research is externally funded. So we have a very sort of applied fundamental research profile in all our activities. In total, we have about 67 research subjects at the university, including the technical and philosophical faculties together. Our division, which is called Machine Elements, is the tribology group, you can say, at the university. And it's chaired by Professor Roland Larsson, and the size of the group is in the range of 46, 47 maybe today people, about 20 senior researchers and 26, 7 PhD students at the moment. We span across the entire range of tribology research, from lubricants and lubrication to modeling and simulation of rough contacts of any tribo system, basically friction and wear, and lubrication, of course, aspects. We do tribo condition monitoring. We work in vehicles and machine component tribology, obviously, biotribology, and a fairly large amount of work is done in the tribal materials area, where we deal with polymer composite materials, metals, primarily, also some ceramics to some extent as well. So we have a wide range of activities in tribology, you can say. Right, so over then to the topic of today, so metal forming. So I'll start with metal stamping or sheet metal forming, just to sort of put this into context and give a little bit of motivation why this is an important area. So if you look at global market growth of metal stamping, there is a prediction of about a $3 billion growth in the period 2019 to 2023, so this year today. The annual predicted growth rate going forward is about 3%, and the 40% of the growth is in the APAC region. So it's by no means a technology and a manufacturing process that is at an equilibrium stage today. So this is continuously growing, and the motivation are sort of highlighted in these 4 words I put at the top of this image. So it is a cost-efficient way of serial production of complex shaped components. It is a fast production process in the sense that you can produce, like I said, complex shapes and relatively large components, and also small components if need be, in a quick and rational way. You get very good tolerances typically, and it's also flexible in the sense that by changing tooling and processing conditions, you can obtain a wide range of geometries, sizes, and also materials in the products that you're producing. If we focus a little bit more on hot sheet metal forming, which is a process that we have been dealing with for a long time in our research group, this is a process that is today the single dominating technology for production of high strength steel automotive components. And it's basically finds its motivation from these three aspects in automotive industry, where you want to typically reduce the weight of the vehicle, you want to reduce the cost, but increase the performance. So this balance needs to be met in different ways, and hot sheet metal forming does that for the body in white structure typically. So that will be the structure, the structural parts that makes up the sort of frame or the body of the vehicle, as you can see in the top right image there. So what you typically deal with are safety components, structural members, such you have B pillars, A pillars, bumper systems, etc., etc. The process itself involves a metal blank. It goes into a furnace, you austenitize the material, you quickly transfer it into a forming tool, and then you form it in a hot stage, and then you quench the material while the tools are closed. So you get good tolerances, you get complex shapes, and you get very good mechanical properties. Another metalworking process that I'll be addressing today is a process known as cold pilgering. This is a tube manufacturing process for producing high strength and high precision seamless tubes. The workpiece material, the tube, they can be stainless steel, can be zirconia tubes or other type of sort of high performance alloys. And the process itself involves a pair of rolls mounted vertically, as you can see in the image here. There is an internal tool that you place inside of the tube called a mandrel, which has a tapered shape. And the idea is that you reciprocate the rollers along the axial direction of the tube, and at the end of every stroke of the rollers, you rotate the tube around its own axis to feed in an undeformed section of the tube. And by that, you reduce the outer diameter and the wall thickness and increase the length of the tube, and also improve the mechanical properties at the same time. Important to notice here is that we have an internal and external lubrication system for this process. So there is lubricant inside the tube between the mandrel and the tube, and there is lubricant on the outside between the rolls and the tube. The most critical one is obviously the internal one, which is typically less accessible in terms of its location, and also there is higher demands on that lubricant in terms of its performance due to the high degree of plastic deformations and resulting temperature that you get from this process, from the manufacturing of the tubes. I will come back to this a little bit later. When I look at metal forming tribology, I typically divide the main influencing parameters in these four categories. So we have the workpiece material, obviously as one part in the tribo system, where mechanical properties, microstructure, and if there is a surface coating or surface state will obviously affect the friction and wear response. Likewise, the counter material, the tooling, plays an equally important role, where typically the surface engineering that might have been applied, the surface topography, and any heat treatment that is done to the material will have a direct impact on the friction and wear response. Then you have the lubricant, of course, in case the process is lubricated, where the type, amount, way of application, and how the lubricant distributes before and during the contact will have a significant impact on what friction level and the wear rates that you will see. And then the process itself, whether that being a press or being a rolling mill or whatever it might be, that's where you decide your operating parameters, velocities, forces, temperatures, etc., etc. So all these combined together needs to be addressed in some way to understand the the response of the metal forming process from a tribology perspective. When it comes to hot forming, which is one of the key topics today, there are essentially 6 main aspects that we and many other research groups are addressing. So friction control is one thing, and it's important here to stress that it's not necessarily a friction reduction that is desired, or minimizing friction. Is to optimize friction at a level that is robust and repeatable, and also at the correct level to obtain the right degree of deformation or performance of your forming process. Minimizing galling, I will come back to that several times during this talk, but material transfer is a main concern in many processes, especially when we're dealing with high performance materials. And this, of course, has a detrimental effect on, for example, surface quality of the component or tool life. So this is an important aspect that needs to be considered in many processes and from many aspects. Lubrication, likewise, of course, type, amount, and so on and so forth is important. And process monitoring with a connection to tribology is also highly interesting, because if you can, the more you can measure and the more information you can extract from a process, the higher the chance of actually being able to detect deviations from the robust process window, and when it starts to deviate and create problems in terms of quality or performance. Just to give you an example of what it looks like, I'm sure many of you are familiar with the appearance of a component and a tool that has suffered insufficient or improper lubrication. So this is an example of just a test geometry. This is an aluminium workpiece, a 6000 alloy, being formed with too little lubricant in this case, so starved lubrication condition. And there's obviously problems on the workpiece, as you can see, a lot of scratching, a lot of wrinkling, and other type of defects that will affect the global geometry as well as the local surface quality of the component. This is often mirrored also on the tooling, where you have a lot of transfer, and the 3D topography image there in the bottom left shows the radius that we are looking at in the photograph above, where you can see that there are tens of micrometers of transfer after only, I think this is 5 strokes that we have taken this image after. So 5 components with insufficient lubrication. So it's a very fast development when things goes wrong, and it requires a lot of efforts to reset the system to its intended state and performance. A couple of words on hot forming and what needs to be considered, and I will give this example for an aluminium alloy, but it also applies to other workpiece materials. Of course, the mechanical properties of the workpiece material at the temperature you are looking for is very, very important. This is given now for a 6000 aluminium alloy, 6000 6060 alloy in this case. And you can clearly see that the mechanical properties drops significantly after about 200 degrees Celsius. And if we're forming the material at, let's say, 400 or 450, there is not much of the yield strength left in the material at that state. That's, of course, one of the advantages to sort of enable forming of complex geometries. But at the same time, that also makes the material very soft and very susceptible to transferring to another surface, the tool in this case. Metallurgical compatibility is another aspect that needs to be considered. So this is the classic Rabinovich chart, which many of you have probably seen, where you have the metallurgical compatibility or solid solubility between metals, where you go from the same metals all the way down to no liquid or solid solubility. So basically you want to be in the yellow range for good performance, and the greener it gets, the worse it is. And if you look at aluminium, it is basically prone to adhering against basically all other metals that you can imagine that you can make a tool out of. So that is one of the challenges that I will give you some examples of very shortly. And then you have other aspects like surface oxide layers, and basically in some cases you have a bad tribological material as the workpiece, aluminium being one, for example, and there are other examples as well. That creates a lot of problems when it slides against something else. On the tooling side, you have likewise composition of the material, the mechanical properties, roughness, and if you do anything with the surface, such as apply a coating or apply a surface treatment like nitriding or something similar. So these are the parameters, except for the operating conditions, that you need to address and need to understand and control to be able to predict the behavior of your system. I have something that I call the galling cycle. This is basically just stressing the fact that this is a reoccurring problem in metal forming, especially in sheet metal forming processes, where you have your stamping process or your sheet metal forming process. You get some material transfer, which may look like this example, the micrograph that you see on the right-hand side. This results in high friction typically, which puts you out of the window of operating conditions where you want to be. It also impairs the surface quality of your component, leading to an interruption of the process when you detect that the quality has reduced too much of your output component or output part. And you need to do something with your tooling, typically cleaning, refurbishing, or resetting the surface state. And then you move back into the forming and the same thing repeats again. This is not a very uncommon cycle that occurs in many industries. So the trick is, of course, to extend the time that you can keep the tools in operation, because in some cases you cannot avoid transfer, but you can delay the occurrence of transfer, or at least minimize the occurrence of transfer. So the idea is to extend the useful time that the tool is deployed into production and minimize the time that you need to spend on refurbishing or cleaning. Just an example, this is what it looks like if you have a hot sheet metal forming tool where you end up with transfer. So what we have done here is the real tool is shown in the micrographs above, where you have a very clear buildup of material. You can also see it is very smooth, very flat. This is typically a sign of that it's been load carrying during the forming operation itself, which of course results in some kind of imprint or scratching on the sheet metal workpiece. We have been able to replicate this. We have done it in several different test setups, so that we have a way of knowing that we simulate the correct wear mechanism. By doing that, we can also evaluate different solutions on how to minimize it. But so you see the lower one is from one of our tribo tests, where you have the same compacted structure as well as this flat and load carrying top surface of the buildup. Just a short note on the tribo testing versus reality. So if you have your global sheet metal forming process as the lower one, you can see the small cutout where you have basically different contact conditions depending on where on the part that you're looking. So you have draw edge tests, you have flat die, so the type of strict drawing tests, there are wedge testing and draw beads and many other different setups that you can utilize to simulate and obtain information from various parts of your forming process. So all of this, of course, requires an understanding of the process and identification of the region where the problem actually occurs, and then addressing it with a proper tribo test. So moving on now to a couple of examples on how to address material transfer in metal forming operations. There are typically three strategies as we are aware of. So there is the surface topography aspect on both interacting surfaces. There is the surface engineering route, where you change the surface typically of your tool, but you can also surface engineer your workpiece. And there's lubrication. So I'll give you a couple of examples on what you can achieve by changing these different parameters and how that may give you a certain response in your system. So I'll start with the tube forming process, or the cold pilgering process that I mentioned a couple of slides back. So we tried to simulate this by using our reciprocating optimal SRV tribometer. We tried different configurations, and we tried a stainless steel cylinder on a mandrel steel disc. So we basically took the real materials and made them into test specimens. And we also tried just a stainless steel ball on a mandrel steel disc. We ran different temperatures to see the effect of temperature, and the other conditions were kept constant during the screening tests. The idea here, or the aim of the study, was to investigate alternative lubricant formulations to replace chlorinated paraffin oils, which are typically not good from an environment or human health perspective. Just as an example, so the chlorinated paraffins, they work really well with stainless steel surfaces. So we have 3 different formulations called L1 to L3, and this is during a load ramp test on the left side. So you can see that we have not extremely low friction, but at least it is repeatable and stable. We also had a couple of sulfur-based chemistries that we evaluated as replacements for this. And as you can see, the lubricant chemistry plays a very significant role in terms of its frictional stability that it can induce on the system. So some of them showed a relatively high friction, some showed an unstable friction, but there were actually some, the blue one in this case, L4, that showed a promising behavior with even lower friction at higher loads compared to the chlorinated paraffin chemistries. In terms of specific wear rates, and this is now the ball sample versus the disc sample. So in white, the bars in white are the ball, the stainless steel ball, and the gray bars are the discs. So obviously the ball wears more than the disc, not very surprisingly. But what you can notice here is that you have a very low wear rate of both interacting surfaces when you use the chlorinated paraffins, and that is the whole point of using those kind of lubricants. The sulfur-based chemistries did not really perform that well, except for one, as you can see, L6, that gave very low wear on both of the samples. So there is a good possibility to screen these lubricant chemistries when you design an experiment utilizing the real samples, real surface topographies that you are interested in studying. And we also correlated these values to real production tests in the rolling mills, and found a ranking which was very similar between actual performance in reality and tribotest performance. If we move on to hot sheet metal forming and lubrication for that process. Now this, I should mention that this process is typically performed in dry conditions. So traditionally, the industry has not been using any lubrication in this process. So basically you have your hot sheet that goes into the tools and you form it hot and dry conditions. We set out to investigate whether lubrication can provide some alleviation to this material transfer problem. And we investigated 3 lubricants, basically. One fully formulated potassium salt-based lubricant. And then that lubricant, it basically consists of an inorganic part and an organic part. So the supplier split that into the two individual components so that we could try to understand which one that actually plays a bigger role, or if that was the case at all. So we apply the lubricant in this case on the tool as it would have been in reality. We dry it at 100 degrees in an oven, and then we also replenish lubricant. So we start with a dried sort of layer of lubricant, and then we replenish with a brush between every experiment. For this purpose, we used a hot strip drawing test that we have in our laboratory. The test conditions, you can see them up there. The important part here is two things. One is the temperature. So we ran the test at 700 degrees Celsius. That's the temperature of the strip. And we also ran the test for 5 consecutive runs with new strips for every test. So we did 200 millimeter sliding on one strip, then replaced the strip, but kept the tools the same, and repeated that 5 times. This is the test configuration. So basically it consists of a strip. This is an aluminum silicon coated boron steel, where the aluminum silicon coating is the problem. That's the one that transfers to the tools. This is pinched between 2 tool steel pins that we load against the strip, and then they slide in the horizontal direction along the strip for 200 millimeters in this case. The tools are not heated in this case, only the strip is heated. So what did we find here? Well, on the left side, you can see the coefficient of friction, the average coefficient of friction from the steady state part of the test. You have 4 different configurations. You have dry testing as a reference to the left, followed by the fully formulated, and then the organic and the inorganic lubricants. So it's quite clear that the organic shows the lowest friction, and the inorganic and fully formulated are more or less the same, and a little bit higher for the dry test. So it seems like the organic part of the lubricant is what provides a friction reduction. Interestingly, not to an extent that it actually reduces the fully formulated oil, or the fully formulated lubricant to a level of the organic. So the organic alone is actually better in that case. To the right, you see the mass loss. And this is obviously now a negative mass loss, which implies that we have a material transfer taking place, plus some residual lubricant that is still there on the surface. What you can notice here is that you have an inorganic, the inorganic lubricant shows very little material transfer, whereas the organic one shows quite significant material transfer, and the fully formulated is somewhere in between. So increasing the concentration of the inorganic part of the lubricant improves the performance relative to the other lubricant, although the dry test shows very little material transfer as well. So this is kind of a status quo in a way, changing to this lubricant. Now, we did take a look at the surfaces afterwards, obviously, to understand what is going on. And what we could see here, now you have a micrograph showing a part of the surface where there is material transfer, and the EDS map on the right side. So you can see a lot of aluminium, and you can see where the iron is around that aluminium, but it also intermixed to some extent. But the lubricant compounds, or the elements belonging to the lubricant, they are concentrated where the aluminium is. So there is an intermixing of the lubricant constituents into the transfer material. And when comparing the appearance of this tribofilm, it looks quite different compared to the dry test. So this is more granule, it's not as strongly adhered to the surface. So there is an added value in terms of the ease of removing the transfer material later on by utilizing a lubricant. So it has to be looked upon from different angles if you are trying to decide whether or not to go for a lubrication strategy in this hot forming process. Lastly, I want to show you what can happen when you combine several of these strategies. So in this case, we have back again to the reciprocating pin on plate configuration in the optimal SRV tester. So we have a pin that is tool steel where we have applied a chromium nitride coating. We have a flat aluminum sample, and we also have different surface topographies on the pin, and we have a lubricant between them also. And this is again a heated test, so we run the test at different elevated temperatures, around 300 to let's say 500 maximum. I'll only give you a couple of examples here. And the idea is to understand what surface topography, coating, and lubricant does together when you apply all of them. This is a little bit of a busy slide, but I'll try to walk you through it. So on the left side, you can see the average coefficient of friction on the top, where you have in dark gray, you have the dry test, and the in light gray, you have the polymer lubricant. So dark is dry, light gray is lubricated. The AR means as received, and PP means post-polished. So what you can notice here is that as received surface topography and dry gives very high friction. You have a coefficient of friction of nearly 2.5. It's very, very strong adhesion and transfer. So basically it's aluminium and aluminium after a short while. Just applying lubricant drops the friction down to about 0.5 or so, which is of course very, very good. But post-polishing, so removing defects on the chromium nitride coating and retaining the lubricant, can reduce friction even more, like 3 times lower friction with post-polishing and lubricant. You can notice the lower curve shows the SA value of the surface for the chromium nitride. So you have about 0.3 for the as received and basically 0.03 or so for the post-polished. When looking at the surfaces, this is quite clear that when you have post-polishing and lubricant, you basically have no trace of the aluminium on the chromium nitride coating. Literally no transfer at all. The lubricant works well, and there is no mechanical pickup. There is an interaction with the lubricant with the aluminium also, so it forms a tribal layer on the aluminium, which is an interesting aspect in itself, and cleanability comes into the picture when that happens. So, but that's a separate study that we are also working on. But basically the explanation is, if you have a hard surface that stays smooth, you have low metallurgical compatibility, and the lubricant that remains in the contact and prevents direct contact, then you can obtain low friction and minimize transfer. So some concluding remarks from this talk is that, first of all, friction and wear, as you all know, are critical for an efficient and robust metal forming operation. And one of the main challenges in many metal forming operations is the occurrence of galling or material transfer. To control this detrimental mechanism, you can, of course, use lubrication, but I also want to throw in this combination with surface engineering. So coatings, treatments, topography, and optimizing that parameter space allows you to find a set of conditions that will minimize the galling as much as possible. And also a note on the tribo testing. So laboratory tests in various tribological configurations, they are very effective tools if you want to screen different configurations or different setups or different lubricants or whatever it may be, as well as providing the fundamental understanding that is required to predict and optimize the system. So lastly, I have just a few words on where I see the future needs for research at present. So tool surface topography has been dealt with for a long time, but there is still work to be done, in my opinion, and aspects such as lay of the topography, texturing, and also the good enough level. So you can always polish and polish and polish and get the smoothest surface possible, but is someone going to pay for that in the end, and will it create an economically viable process? Maybe not. So a good enough level is important to find for many processes. Likewise, coatings, there's an endless possibility when it comes to coatings, to compositions, but also thickness, deposition techniques, etc., are variables that can be used to optimize and select various type of surface coatings that can be a tool in the pursuit of a robust forming process. And when it comes to lubricants, the wettability of the surface, or wetting, how the lubricant wets the surface, how you provide easy shear, what is the mechanism? Is it a chemical reaction? Is it a solid lubricant or something else? Cleanability, as I mentioned, highly important. You want to remove the lubricant after the forming. And also, how do you get the lubricant there in the first place? This is also a very important aspect. So with that, I thank you for your attention. I look forward to the Q&A a little bit later in this session.
Thank you so much for that, Professor Yen. That was a really interesting talk. So in terms of an agenda, we're going to hand over to Dr. Schneider from Optimum, and then we'll come back to Professor Yen regarding the Q&A session. So
Absolutely.
Professor Schneider, we are ready for you. Thank you very much.
Can you hear me? Yes. Okay. I'm very pleased to be with you and this evening after this very, very exciting presentation. And my name is Schneider Amena. I work in Munich by Optimal Instruments, and in the next few minutes, very shortly, I'm very pleased to inform you about the newest development we have done in the case of investigating of coolant, metalworking fluid, especially, of course, coolant because of the newest development we have seen and because of the demand of them from the market. As this slide is summarize few things from the latest literature. As well known and Professor mentioned already, there is a very big challenge in the formulating of metalworking fluid, especially water-based. Of course, the challenges are many, many different, like environmental, health care, and the formulation must be very stable and very, very long time of life. But all these things, they are, of course, various tests for check them. And in these few minutes, we are concentrating on the tribological performances of this metalworking fluid, because, as you have heard, we have to make a protection of the material, and rubricity must also be given. And for the formulating of this metalworking fluid or coolant, it is really, really a challenge to find a right type of antiwear and and EP additive to work on ferrous and non-ferrous material. As you know, different reactivity, different tribochemistry are working here in this case. It depends on the material of the working tool and the working piece. And they are symmetry. The challenge is really to have a metalworking fluid which works really proper with both materials, and therefore we have seen there is a need for a tribo test method for a machine, and we developed this for customers of us or for the future customer to achieve these challenges. Here you can see in this slide very shortly a cross-section of the design of this new setup for the rotation motors. That is the rotation motor of SRV. You can see that the fluid is the metalworking fluid or coolant will be supplied directly on the test contact. And of course, we could manage to have also on the drain a very good temperature sensor to control the temperature differences. And here you can see how the machine look like, how a machine or this setup look like. It's very, very user-friendly. And you can also, this is a disk, for it is the under specimen. You can run 6 tests on one piece, and you can also see, you can change the point from the point to the line contact if you want, and it is the mushroom shaped, and the bulk here we can have different combination of the geometry. And then you can, here you can see how the preparation of the metalworking fluid was prepared in the laboratory by us. Just mention here shortly, there is no circulation. Otherwise, you can see here the wear particles. If you make a circulation, you have the wear particle on your contact. It is a one drain, and then 6% of the metalworking fluids were prepared. We don't go very
For that, I'm not sure what's happening. Hopefully, Dr. Schneider will be able to join us again.
Okay, sorry, I am here again. Sorry.
Oh, perfect.
Sorry, thank you. I'm sorry. I was too fast. Sorry for that. Here you can see the test matrix we have run. There is a lot of possibility to have the under specimen and upper and under specimen. We have steel and aluminum. We have chosen steel aluminum as the workpiece, and we had 4 different materials, steel materials for the tool piece. And of course, I don't go in the details for the parameter. We have search and find the perfect parameter for investigating. And
Sorry for the slight technical issue here, all. Let me just be back with you in a moment. Right. Emily, can you come back on stage, please? Okay.
example for I show you a few examples about the reputation of this test method and the ranking of the fluids. As you can see, the reputation is very, very good concerning the, we have here measured the coefficient of friction for the coolant C, and the material were steel and 116 mangan chrome 6. And the wear volume could be measured also online. And we have seen that the online measurement was very nicely correlated with the measurement under microscope afterwards. And the temperature development is really, we don't concentrate on that because it was only 1 + 1 - 2 degrees Celsius, which is obvious. We had a very high 49% water. The coolant effect was well done. You can see for the other example that really absolutely the repetition is given very nice values of the wear measurement online as well. And here you can see, I don't show all the 42 examples. Of course, I have chosen few of them to go forward in the short time I have. You can see the coolant A, B, C, how we could rank them very nicely. The coolant C is absolutely the best one here concerning the in combination of steel and 20 mangan chrome 5. And then the other example is for steel and 16 mangan chrome 5. Again, the coolant C is very constantly, as you see here, the coolant B is not so good, and coolant A even has low coefficient friction value, but the fluctuation and the stability of the field is not so given like as coolant C. And the 415 chrome vanadium 3, which is a very, very hard and very good tool material, typical tool material. All the three have very good low coefficient of friction value, but the most stable one is again B, and in this case would be C, and also B will be a good one. And as we calculate again to see the repeatability, you can see the other the values, how the repeatability is really given with this method. Only in one case. In this case, we had one outliner, and the operator should make this test a third time. And you see that in all combination, the coolant C has the lowest value of coefficient of friction, followed by, of course, by the wear values. And change now from the steel to aluminum, which is very important and interesting. Okay, we have seen that repeatability is absolutely given also with this combination, and the wear values are straightforward, a little bit higher than in the case of steel. But we could not make that kind of nice ranking between A, B, C coolant, and we have made a look in the first. We made ramp from 0 to 3.15 meter per second, the velocity which we have done also for the steel. And we have seen in the case of aluminum, we were too fast. We have to repeat all the tests under 1 meter per second. And we have done it recently, and we could see that in this case, even we have reduced also the normal road, we can have a good differentiation between and could make a ranking also for aluminum as working material. And you can see even maybe the coolant B would be better for aluminum. And of course, the operator or the user can say this differentiation is not enough for me. You can change easily your parameter. That is what you can really do very nicely with the SRV. You go to higher load, you change the temperature, and in this case, not the temperature, you change the velocity, and you can have differentiation. And that is the summary of this short work. We have long work, but short presentation, that you can see that this new setup can help you to rank your metalworking fluid or your coolant in different application and very near to application with different material as working tool and piece, working piece and tool work material of tool. And you can see that you have seen that the repeatability was very nice, as we are used by SRV. And of course, for the aluminum, few works must be done forward in the future. You have to optimize the parameter. And we hope that this tool will help the metalworking fluid people, producer, to achieve to make better and better metalworking fluid or coolant for the future. That was my last slide, and I would like also to thank you for the chance to give this presentation and for your attention. Happy to answer your questions.
Thank you so much for that, Professor Schneider, Dr. Schneider. I think just a quick question from the audience. What was the value of the sliding velocity? Was it cutting or sliding?
Question to me or to Professor?
Yes, to yourself, I think.
Can you repeat the question, please?
It's on the screen, but what was the value of the sliding velocity?
3.14 meter per second for the steel, and we mentioned that it was too fast for aluminium. We had to reduce.
Sure.
We ramped from zero. I did not go to details. From zero for in 10 minutes, you go from 0 to 3.14 and stay for 20 minutes at this velocity. Altogether, you had 30 minutes of test time.
Brilliant. On that note, we'll go over to Professor Yen, and we'll take some of the questions. So I believe one of the first questions is, what are the main differences in performance-wise between silicon and perfluorinated lubricants, especially in cold temperature applications? We have noticed the silicon lubricant is lower viscosities. Lower viscosities tend to deplete more than the lubricant around the same viscosity.
That's a very, very interesting questions, and also rather specialized lubricants. I would say it's difficult to generalize this answer because it also depends a lot on the system itself, like the interacting materials, whether this lubricant is provided in form of a grease or if it's a fluid. But I'd imagine that if it's a depletion problem, so that it doesn't remain or stay in the contact in the same way, I'd imagine that the compatibility with the surfaces might be one aspect. So how well it wets the surfaces, if there is any other type of physiochemical interaction that may play a role. I'm also thinking about that these are rather different in their chemical structure. So PFP, of course, is sometimes used in very, very demanding applications. Well, silicone lubricants as well, for that matter. But I would probably start with the materials, the compatibility between surface material, surface texture, roughness, and the lubricants to investigate it from that perspective. That's just my spontaneous thought on this.
Thank you very much. The next question is, it's interesting that the lowest coefficient of friction showed by the organic lube translated into the highest material transfer, which you showed that normally leads to higher coefficient of friction. Do you have any comments on that?
Yeah, there's a very sharp eye notice that. This is something that happens in certain cases where transfer doesn't necessarily translates into high friction. What happened in this specific case is that, as I pointed out in the EDS mapping, the presence of the remaining lubricant constituents were also found at the same place where we had the most transfer. So what we found was the formation of this tribofilm, which is a mix of the lubricant and the transferred material, helped to reduce friction, but for that to happen, for this transfer film or tribofilm to develop, it also requires the occurrence of material transfer. So that was the origin of that.
Brilliant. Just move on to the next question. What is meant by AR or polishing of lubricant?
Yeah, so AR in this, the abbreviation was as received. So the surface topography of the coating as it was deposited on the tool steel substrate.
Sure. And I think there's a second part to that question. Why do we need to polish the coating?
So in this case, the coating was deposited using PVD technique. So that very often leaves some kind of surface defect in form of droplets or other type of topographical unwanted features. So what you do when you polish is basically you get rid of these defects at the very outermost surface of the coating to have a more smoother surface with preferably only some pits left, if anything, rather than something protruding out that can act as a sort of a scratching tool on the workpiece.
Sure. And our next question is, have you studied solid lubricants?
We have in several contexts. If we talk about aluminium specifically, which is where we have done most of the work, we have dealt with graphite and hexagonal boron nitride, for example. One of the key aspects here well, there are actually two things. One is that you need to ensure that the solid lubricant actually remains between the surfaces. In that way, for example, hexagonal boron nitride is very inert and it's very good for that purpose. That's also the drawback, that it's very easy to eject the particles out of the contact because they don't really attach to anything. Graphite is better in that way. The second aspect is to look at the particle size of the solid lubricant versus the two rough surfaces that you put in contact. If you have too small a particle size and two rough surfaces, the particles typically do very little for improving the friction or to prevent wear. So you need to optimize your particle size and surface topography to get the most out of that system.
Perfect. And I believe that was the last question for today. So thank you very much. Thank you very much for your questions. Thank you to the speakers for a great interview and engaging talk. Thank you for sharing. We really appreciate it. We'd like to thank our partner, Optimum Instruments, for supporting this webinar. As a reminder, please do visit our website where you will find the recording for this keynote. We will organize our next webinar on the 23rd of February. So please do stay tuned on our website, emails, and LinkedIn for further updates. We also have a fortnightly newsletter, which is called Modern Surfaces. Please sign up on our mailing list and you'll receive this. We also ask for your support to take the time to advertise these lectures to your contacts. So on that note, thank you for joining us, and we hope to see you next time. Again, thank you for joining us today, and enjoy the rest of your day. Thank you so much.
Thank you very much.
Bye-bye.
Bye-bye.
Bye.